To reinforce the idea of a total EMF, let's revisit the sliding bar example. Here we have the rectangular loop again with the sliding bar that moves to the right with a uniform velocity u, but this time it's placed in the time-varying magnetic flux density with the B field being given by this expression here. So it's still directed in the Z direction. It's still uniform, but time-varying. So let's make a note of that. B is uniform with space, but time varying. And as before, the bar starts from x equals 0 at time equals 0, and we're asked to find the total EMF between terminals 1 and 2, which are across the resistor. So here let's use Faraday's law directly to find the time-varying flux. So we'll try to find the time-varying magnetic flux by, first of all, integrating the time-varying B field over the surface S. Now, since the B field is uniform, we know that we can just pull B outside the integral and simply take B of t or the Z component of B and multiply by the area of this loop at any point in time. So we realize that since this bar is sliding over to the right, this area in here is actually a function of time. It's a linear function of time because the width of the rectangular loop is a linear function of time, whereas the height of the loop is obviously unchanging. So we can write that here. Let's first write out Bz. So this is B naught times sine omega t. And then the area is the length or the height of the rectangular loop, which is labeled L in the diagram. And the width of the loop is x naught, which is in itself a function of t. So we can see we're going to have time dependence both with the area of the loop and the B field that's passing through it. So this seems to fall into the category where we're going to have both a transformer EMF contribution as well as a motional EMF contribution. So let's apply Faraday's law and compute the derivative of the magnetic flux with respect to time. So we're going to have a minus sign here, and let's work out the contribution of each quantity here. So the first thing that we need to do is, well, we need to take the derivative, but we're taking the derivative of a product. So we're taking the product of B naught sine omega t with L times x naught of t. So it's a product of two functions that are in themselves functions of time. So we need to apply the product rule. So let's apply the product rule for differentiation here. So what do we do in the product rule? We take the derivative of the first function and multiply by the second, and then we take a derivative of the second function and multiply by the first. So the first function here is B naught sine omega t, the term that's been underlined. So the derivative of that is B naught cos omega t, because we know the derivative of sine is cos, but because of the chain rule or the fact that we have an omega t inside the sine function, that needs to come out. Then we multiply by the second function, which is L x naught t. Right, so that's the first part of the product rule. The second part of the product rule is now we take the derivative of the second function and then multiply by the first. So the derivative of the second function is, well, L is a constant. Then we have to take the derivative of x naught, which is a function of time, and then multiply by the first function, which is B naught sine omega t. And that ends our product rule. So let's have a look at each of these terms individually. If we look at the first term here, we recognize this term in green is actually the transformer EMF. It arises because of the time-varying flux that's passing through the loop. So the loop area is over here, and it's the time-varying nature of the B field that is causing this particular component of the EMF to arise. We have defined previously the transformer EMF as the negative surface integral of the partial derivative of B, because B could potentially vary with both space and time. dot ds. So in this case, again, because B is uniform, we don't need to worry about this dot product. We can just evaluate this as the time derivative of Bz multiplied by the area of the loop, which in this case is B naught cos omega t. Again, the omega comes out because it's inside the cos function, and then we multiply by the area, which is L x naught of t. So from our definition of transformer EMF, we see this indeed is the transformer EMF and only the transformer EMF. That means that the second component here must be the motional EMF. To see that, let's apply our definition of motional EMF. We know that the EMF due to motion is the closed contour of U cross B dot dl. And again, while we integrate over the whole loop, there's only one section that's really important to us, which is the moving bar section. So we'll integrate from point 3 to point 4. Our velocity, which is in the x direction, and a value of u. We cross that with the B field, which is z directed, and also a function of time. And then we need to dot this with dl, which in our case was y hat dy. So if we evaluate this dot product here, this is just minus b naught u sine omega t y hat. The negative sign comes out because x hat crosses z hat is minus y hat. And then if we dot this with the y hat dy, then the dot product is going to go away, and we can carry out this integration from 3 to 4. We know that that length is just L, so this EMF is going to be minus B naught times L times U sine omega t. And indeed, that's what we have up here, because this term dx naught by dt, this is a derivative of position with respect to time, that's velocity. So we notice a match between the motional EMF above and this one down below. So we see that indeed this, starting from the definition of Faraday's law, this will always lead to the so-called total EMF, but we could have separately applied the definition of the transformer EMF and the motional EMF to find that. So this concludes our discussion of total EMF. Next, we'll be moving on to an important concept known as displacement current.